Hi guys, so here are typical problems for the MCAT that relates to geometrical optics. So here is an example. This is given to you, and I think they say that the image that you get here is real, and they want you to find the focal length. So if it's real, that means the focal length is going to be positive, and the image here, if it can be displayed on a screen, that means it's real and upside down. So that means we have this situation here. So maybe it's going to be an image that's going to be enlarged. It's going to be real because it can be displayed on a screen, and it will be upside down. If the focal length here, twice the focal length, the object is inside the distance equals to twice the focal length, so the image will be enlarged. And if the distance is just twice the focal length, the object distance, so then the size will be the same. And as you move away from the lens, you see the image get smaller. So that was just a quick review. So you're gonna just apply the thin lens equation. So 1 over the object plus 1 over the image equals 1 over the focal length. So you just substitute the distance for the object is d, so it's going to be 1 over d plus 1 over 2d equals 1 over the focal length. And then you solve for f, right? So multiply by 2 here, multiply by 2 here. So you have a common denominator. So 2 plus 1 is 3 over 2d equals 1 over f. So the focal length in that case is 2d over 3. Okay, and that will be like a multiple choices type of problem. So 2/3 of d. So d is here. That's going to be here. So 2/3. So 1, 2. So that's going to be here. That's going to be the focal length. That's the focal point. So you see that it's inside the twice the focal length. So that's going to be twice the focal length here. So you expect to have an enlarged image, right? So you can do ray diagram. It's going to go, so that's going to be d. That distance is here is d. So that's going to be the focal length here. So parallel ray, it's a parallel ray. So just to review quickly, you have like a ray here. It will want to go through the focal length. And if you have a ray going for the center, okay, so you're going to get upside down image. Okay, it's going to be real. It's going to be upside down. And it's going to be enlarged. And again, you have many rays. These rays won't reach the screen, but the other ray here will. Okay, so that's just a review. And then, okay, so let's see another question here. Also multiple choice. They they ask you what's the best graph that illustrates the Finland's equation. So I over O versus I over I, over 1 over I. So you have the Finland's equation. This is the Finland's equation. So imagine that 1 over O plus, that will be the object distance, that will be the image distance equals 1 over F. So that will be our Y. That's going to be our X, the dependent variable. So you're going to have Y plus X equals, and that's just a constant, so I'm going to call that M. So Y equals minus X plus M. So you see, this is the equation of a straight line. That means that minus here is just minus 1. That's the slope. So it's going to be minus 1x plus m. Okay, so that means if you have y here and x here, when x equals 0, you have m, which is 1 over the focal length, and the slope is minus 1. So it's like a diagonal here. Makes a 45 degrees, so it has to be something like this. So the solution is A. Okay, so that's number 2. Number 3. See. So let's see number 3. Let's see number 3. Number 3, I don't have it. Do I have it? No. So number 3, the question is find the magnification here. The magnification. So that means the ratio between the size of the image and the size of the object. So we call that magnification. It's a factor, is minus, by definition, the distance to the image over the distance to the object. So that's going to be minus, image is 2D over object D. So it's going to be minus 2. So magnification, so minus means it's going to be upside down. 2 means it's going to be twice as big. So the ratio between this and that, so is 2. So this one is twice as big. Okay. So number 4. So now we move that object to the left. So we move the object to the left. And we want to keep the image on the screen. So how you gonna move the screen? So if you move the object to the left, you move it toward infinity. So remember that if the object is really far away, you're gonna see the object here at the focal point. So that means that you have to bring the screen closer to the lens. Okay, so if you go back to the app, the question is, if you move the object farther away from the lens in this direction, you see that the image is getting closer and closer to that focal point here. If you move it here really, really far away relative to the focal distance, really far away, meaning at infinity, that here will just be a point here at the focal point. That the image here will be moved there. So the screen has to be moved toward the lens. So moved toward the lens. Okay, so that was for number 4. Let's see if we have a number 5 here. So the focal length is d over 2. How far away from the lens should we place the screen? So it's the same situation. Let's see. So we are still working on with that figure here. So now the focal point, the focal distance is d over 2. And the object, so they try to confuse you with the wording, but they're just asking where, what's going to be I, the distance of the image. The object is still d. And the question is just find the distance of the screen. So we're going to have 1 over the screen, distance to the screen, so the image, plus 1 over d equals 1 over f, so it's going to be 2 over d. So 1 over I equals 2 minus 1 over d. So it's going to be 1 over d. So I equals d. Okay, so now we place the focal length is d over 2, and that's going to be the answer. So the answer is C. Okay, so number 6. So it's same situation, but now we replace the lens by a diverging lens, okay? So diverging lens meaning the image has to be virtual. I don't know what's happening. So now we take a diverging lens here. Okay. So you see with a diverging lens, the image has to be on this size, which means the distance here to the image will be negative. The focal distance is negative, and that's going to be the object. And the image is virtual, is upright, and is reduced with a diverging lens. So what are they asking? So focal length now equals minus 2d. So let's find the object distance is d, and they want you to find the image distance. Okay, so you're gonna have just easy, right? You apply the thin lens equation equals minus over 2d. So you're going to have 1 over I equals minus 1 over 2d minus 1 over I. Okay? Minus 1 over d, sorry. So that's going to be minus 1 minus 2 over 2d, which is minus 3 over 2d. So you have to put at the same denominator. So you get I equals minus 2d over 3. Negative means that the image is located on the left of the lens, right? So it's going to be virtual and located to the left of the lens here. And in that case is 2d over 3. Okay, so number 7. Still the same image. So they want you to, so it's still the same situation here, but now they want how far to the left the lens should be. Should the object be placed to be a magnified real image? So let's go back to a so this is diverging, this is converging. And if you want to have an image which is unmagnified, so the same size, so you have to place the object here at a distance exactly twice the focal distance. Twice the focal distance. So if the focal length is d, so you have to put your object at 2d. So that will be answer B. Okay, so if this is G, so then that's going to be 2D, and you see the image is real, upside down, and unmagnified, so the same size. So these are other kinds of problems. It's telling you that white light is a mix of all the colors in the rainbow. So if light travels in a vacuum, so all the colors, they're going to have the same speed and they're going to be all mixed. But when light goes through a dense material, so blue light does not have the same speed as red light when it's traveling inside that medium here. So blue light will travel slower than red light. So because it's traveling slower, that means that for blue light, the index of refraction will be larger and it's going to be refracted more, okay, when entering and exiting. So for example, quartz, you see blue light is associated with a larger index of refraction. Red light, the index of refraction is smaller. That's how we can use a prism to make rainbows. But in the vacuum, and about the same in air and vacuum, almost the same thing, they all travel at the speed of light. Okay, and that's going to be the speed of light. It says in a vacuum, they all light travel at the same speed, and they have, regardless of their frequency, they will travel at the same speed. And just to review that, when there is refraction, so you go from fast to slow, you see the frequency does not change. Okay, you don't see if you shine a laser through the window, you still see the same color, so the color does not change. If you look through the window and you see the trees, they still have the same color, but the wavelength here will be smaller because the speed is smaller. So if you measure the speed here, that will be the speed of light, and inside there the speed is smaller. It's going to be 2/3 of what it is here. So the wavelength has to be decreased by the same ratio. And blue light, even smaller wavelength here, because the speed here is even smaller than red light. So the wavelength gets smaller and it will have more refraction. So it will bend more toward the normal. Okay. Just crashed. White light, not color light. How can this be explained? So if you see white light, that means the index is almost 1, right? So that means there is no refraction. So it's the right answer. So the light does not travel at different rate of speed. That's the answer B. Okay, because in air, it's like almost like vacuum. All the colors, they travel at the same speed. So that's why we're going to see white light. Okay. So it's a little bit tricky. So that's for number 9. Number 8, number 9. So monochromatic light, that means one frequency, one color, what is refracted by a prism. So you see that according to here, when you go toward the blue, the wavelength gets smaller, the frequency gets larger, and as the wavelength gets smaller, you're going to have more refraction. Okay, and that means the speed of light will get smaller. So the answer will be the shorter its wavelength, the more it's refracted. So blue light, if you compare blue light or violet, here you have violet light, you have smaller wavelength than red light, and blue will be more refracted than red. So the answer is C. And here they just want here, what's the question? So here they're asking you which light will be the most refracted. Green through dense flint, violet. So what you are supposed to do is to use that table here, and you are looking for the answer, right? So it says green, dense flint. So dense flint is here. Green, you have the index of refraction is going to be 1.674. So that's very large. And then violet crown. So violet is here. So that's going to be 1.538, which is smaller than 1.674. And then you have see red through ice. So red, forget it. Red is not very much refracted, but let's see, ice 1.306, so no. And then I'm lost. Blue for quartz. So blue is here, quartz 1.551. So the most refraction that you will get is green light going through dense flint. So that was an easy equation. It's just for you to read the table.